It's been over 20 years since we last had supersonic flight. In fact, the Concorde's first flight was in 1969, and today, still, the flight time between New York and London is the same as it was about 50 years ago. So the world around us has changed quite a lot. Blake, why not planes?
I think it goes back to the story of how innovation works and how it doesn't work. The first 50 years of flight, from the Wright brothers through to the introduction of jet travel in the late 1950s, every step forward, which, by the way, every step forward was a step in speed, was driven commercially. Douglas built the DC-3 because he saw a large market opportunity for that specific airplane. Boeing brought the 707 to market, the first really successful jetliner, again, because they thought they could sell a lot of them and that the product made sense. And then in the 1960s, we lost our way and we shifted from a commercially driven model of innovation in aerospace to a national prestige driven model. So we did Concorde for supersonic and we did Apollo for space exploration. And it's a little bit heresy to say this as an aerospace person, but I think both were terrible ideas and we shouldn't have done them. And I think Apollo killed space exploration and Concorde killed supersonic flight. Because what happened was, instead of having to have an entrepreneurially led, commercially led approach where the product has to make sense and it has to be worth developing and costs matter, we had sort of unlimited government resources poured into government-spec projects. And so Apollo, obviously, there was no business model for going to the moon. Nobody even talked about it. But Concorde was in some ways worse because it pretended to be commercial. And yet nobody thought hard about the economics. They were just trying to beat the Russians. So here's a 100-seat airplane. By the way, 100 uncomfortable seats. You might mistake them for like seats out of like Southwest or Ryanair, where adjusted for inflation, the fares ended up being about $20,000. And so if it's the 1970s or 80s, you can't find 100 people that want to drop 20 grand to go somewhere really fast in an uncomfortable seat. It never made any sense. It was dead on arrival. And yet the consequences of this were just tremendous. On one hand, the industry learned all the wrong lessons from Concorde, and they concluded that supersonic flight was not viable, not that Concorde was not viable. So those two things got equated. And worse, because now this is a matter of like national prestige, now geopolitics got involved, right? And so the American competitor to Concorde was canceled. And after that happened, then we did the stupidest thing that we've ever done in the history of regulation, which is we banned supersonic flight in the US. And that, I think, if you pull on that thread, it takes you all the way to like the collapse of Boeing that we're seeing now. Because literally it was not possible to build the next better product, because the next better product would have been a supersonic private jet that was designed to carry a couple of wealthy people coast to coast. It would have been small, simple, and that would have started off the next innovation cycle. And had that happened, we'd all be going Mach 5 by now. But basically, they banned the minimum viable supersonic jet, and the result was half a century of stasis and regression. And I think one of the things that happened is it led to a whole generation of talented people who didn't even go into aerospace. Like, one of the things that's really hard in building Boom is actually, I think the single hardest thing is the team. And the reason is there's like a missing generation of talented leaders. And they all work at like Google and Facebook and Amazon. And they don't even work in this industry. And by the way, I was one of those. I had to switch industries.
Why did they ban it? Why did they ban supersonic air travel?
So every bad regulation has a moral cover story and then a real story that's secret. And the moral cover story was sonic booms are bad and we have to protect the public from sonic booms. It's bullshit, but that was the moral cover story. The real story was it wasn't yet obvious that Concorde was DOA, and the American competitor had just been canceled. So now we have to protect Boeing from the European Concorde.
It's funny, too, because the thing that most people were concerned about is the noise. I'm assuming the sonic boom. But in reality, They just banned the actual supersonic flight, which was not the core issue. They actually banned the wrong thing. And that's the thing that prevented the innovation, is if they actually went for the source issue. It was like, these planes are really loud. We don't want them breaking windows or hurting people on a day-to-day basis. But in reality, they just stopped the entire thing, even though that's not always the reality. And you guys actually managed to solve that.
Yes, I think that's right. But I think, so I don't know the following with certainty, but my suspicion is that was not an innocent mistake.
Mm-hmm.
And that the reason it was a speed limit, not a noise limit, is because if it had been a reasonable noise limit, Concorde would have passed.
Limitless
I don't know
Nation.
that. I've never heard of Concorde Sonic Boom. I'm too young for it. But by the way, the booms, you can make a really bad sonic boom. A boom is sort of like the wake of a boat. And so if it's a big boat and you're right next to it and it's going fast, there's going to be a big wake. But by the way, if the boat's like on the other side of the lake, the wake is very small by the time it gets to you. And waves fall off with the inverse square law. So if you double the distance, you end up with a quarter of the intensity. And so if you're flying supersonic at 60,000 feet, the boom is attenuated. And as we can talk about this, we can get into this, but also there are ways there are ways you can, that the boat metaphor breaks down. You can make the wake make a U-turn and leave such that the wake never hits you.
So the idea behind like why we don't have supersonic travel, it's some combination of just terrible reasoning with regulation and also a bunch of inertia as well.
Yeah, I think a bunch of inertia. The minimum viable product being illegal, I think, is a big part of the story. I think that there's also a story about kind of what happened with ambition in the early 70s. And I think there's a website called like WTF Happened in 1971, where a zillion different trend lines all changed at the same time that were very negative for progress. So for example, up until I think about 1970, energy production and consumption per capita was on an exponential growth curve. And then in 1970, there was an inflection point and it switched to a shallow linear curve. Productivity per capita, a similar story. There was one curve and then the curve changed. So many, many different things went wrong in the 70s. And I don't know exactly what the cause is, but one thing that I think is sort of in there is we became less ambitious and optimistic about the future. And so the original environmental movement, I think in many ways was actually just anti-progress. And the environmental cover story was what actually led to the creation of the supersonic ban. And it was one of the first killing supersonic flight was in some ways one of the first victories of the environmental movement.
Interesting. We are talking to
now I mean, this is like, again, I don't mean to malign all of environmentalism. Like I believe in clean air and clean water and, food that's safe and airplanes that don't crash. But sometimes these things get glommed together, particularly when there's an industrial interest behind the scenes.
Right.
And you can end up with an anti-progress take for attached to something that sounds good.
We're talking to Blake Scholl, the founder of Boom Supersonic. This is a company trying to do something that hasn't been done in over 50 years, which is to make a commercial airliner that goes really fast. Commercial air technology, as we said, hasn't improved in decades. The Concorde, the first and only supersonic commercial airplane, did its last flight all the way back in 2003. Since then, the industry has been pretty stagnant, but Blake here is trying to fix that with his company, Boom Supersonic. Blake, what's your secret? What are you able to do that no one has been able to do over the last 20, 30 years? Why are you the person pushing forward on this frontier?
It's very bizarre for me personally, because I don't have the resume for this. I'm a software engineer by training. I spent the first 15 years of my career on the internet. Everything I know about aerospace, I'm essentially self-taught on. And all throughout, especially the early days, it was very bizarre for me personally to be like the one working on this. Cause I'm like, my self-image is not like, oh yeah, I'm the guy that's going to crack the formula to create a supersonic renaissance. Like what? It's kind of crazy. I think it came down to, I looked carefully when no one else did. And I think the result, I think the story is really about the bystander effect. in the Valley in particular, we all get taught, if your idea is a good idea, there are likely going to be several other good teams already working on it. And if no one else is working on your idea, it's probably a bad sign about the idea. And so as supersonic flight sort of falls victim to this sort of bystander type thinking, it would be so obviously great if we could fly supersonic. Nobody's doing it. Therefore, it must be a bad idea. And the internet back 10 years ago when we were getting started was full of plausible stories about why you couldn't do this. But none of them stood up to careful analysis that anybody with a spreadsheet and a web browser thinking from first principles couldn't debunk. So what was the story on Concorde? Like we said, it was, at the outset, here was a product with no product market fit. What would it take to create something with product market fit? Well, you'd have to get the fares down to the point that more people could afford it. You'd have to get the comfort up such that people would want to fly on it repeatedly. And you'd have to have overall economics on the airplane such that airlines could make money, not just on a couple of routes, but at scale such that it's all worth adopting and it's worth developing. Okay, so what could that product be? And could it be created? And could it have a big enough market even with the supersonic ban still in place? And so I think it took me 2 weeks to have the key idea, which is let's do a supersonic seat that matches the economics of a flatbed in business class, because that's a gigantic market of people already paying top dollar because they hate the flights so long and they want to sleep on them. And then how much would you have to beat Concorde by on fuel economy to create a supersonic seat with the economics of a flatbed? All the information you need for this to answer that question is on Wikipedia and Seat Guru. And it's a very simple spreadsheet. And the answer was less than 10%.
You mean 10% savings of
10%,
fuel?
10% fundamental efficiency improvement versus Concorde on fuel burn per seat mile would let you get a supersonic seat that's a good size with kind of an overall economic profile that would match business class. And so once I saw that, I'm like, okay, well, how much better was the 787 versus the 777, and how much better was the triple versus the 76? No, they're like typically double-digit improvements generation to generation of airplanes. So can we not find 10% versus 1960s technology? Like at this point in my journey, I didn't know anything, but it seemed plausible, and I sort of decided at that point, well, if I actually want to have a shot at doing this, I need to get way smarter. I need to build a dream team. I need to know what the heck I'm doing. And so I spent a year I went all the way back to calculus and physics, which I hadn't had since high school, and just tried to rebuild a whole new stack of knowledge so I could actually think about it much more deeply.
Okay, so a guy coming from the world of the internet, I think the reason why you had confidence, if I'm hearing this, the reason why you had confidence that you could take on this seemingly monumental challenge that no one had done before was that the margins are just so good because so much margins have been left on the table and no one's picking it up. And so while it's still a daunting feat, because no one has really tried, the opportunity, it just grows every single year that that no one actually tries to actually tackle this.
I mean, I think that's true at the market conceptual level, but I want to put a circle around confidence, because I had no confidence on day one that this would work. In fact, I was pretty confident that it wouldn't work, and I thought it was pretty unlikely that I would personally be able to be the leader that would do it. I mean, I think the largest team I'd ever led was 10 or 15 people. Mm-hmm. The startup that I'd founded and sold to Groupon hadn't really been a success. It was kind of an acqui-hire. But a premise I had, a couple premises. One was the only way I could know what I was really capable of doing was to pick something that inspired me so much that I would give it everything I had, and that my desire to make it work would exceed my insecurities, and I'd be willing to reinvent myself in order to see if I had a shot at making it work. And I also kind of thought about okay, what if it doesn't work? And how would I feel then? And it was very important. By the way, when I'm recruiting people to Boom, particularly in executive roles, a thing I say to all of them is you have to be open to the possibility that the whole thing doesn't work and that you are personally still going to be okay. Because if you don't do that, if you're afraid of failure, if you're not okay, if you wouldn't be proud to fail at this, then you shouldn't come. And so I sort of like mentally accepted failure is the most likely outcome. I would rather be an entrepreneur that tried this and failed than one that never tried.
This mindset is something that inspired me and made me want to have you on the show. I think we're going to get into your background because the story is pretty incredible. But first, I want you to explain to everyone how this actually works. Clearly, we've advanced quite a bit in the last 50 years since the Concorde was created. But I kind of want to get into the tech stack specifically about what you realized that you could do that everyone else failed to realize in the past, and how you're actually able to make a supersonic plane in the year 2025 as a private company. I think this is the first private company to offer commercial supersonic flight. So I kind of want to get into the technology stack of how this all works.
Yeah. So maybe I should say a little bit about where we are in the journey, and I can break apart the technology stack.
Awesome. Yeah, please.
So earlier this year, we flew our prototype test airplane called XB1 past the sound barrier, actually 6 times across 2 flights.
And you actually streamed that. And I would encourage everyone to watch because it was pretty amazing to see this airplane and your test pilot fly at supersonic speeds multiple times over.
Yeah, the live stream, which by the way was filmed on an iPhone and streamed on Starlink
So cool.
at north of Mach 1, was just the crew that did the live stream was just phenomenal.
Mm-hmm.
So it's a fun, particularly the first supersonic flight. It's a fun live stream. I'd recommend that one. So the XB1 airplane is sort of a 1/3 scale technology proof of concept, and we built that because we knew we didn't know everything we needed to know, and only by building, going design, build, fly, learn, would we actually be able to learn 100% of the lessons that we have to learn to build a supersonic airliner. And I think it's important to say here, no one's done this in 50 years, so you can't just go hire a team that has relevant experience. The only way to have a team that knows how to build supersonic jets is to go find the best people you can find and let them go have a practice run at it so they get the experience. So that's what we did on XB1, and we basically said the rule for our first prototype and our first production airplane is we will only use technology that has been proven safe, reliable, and efficient elsewhere, where the regulators have a precedent for approving it. So like all the fundamental tech is like basically pre-approved, and it's the design and the product concept that are new. And so what does that mean specifically? The big 3 things that have sort of moved forward since Concorde are aerodynamics, materials, and propulsion. And so from an aerodynamics perspective, it used to be that all development was done in wind tunnels, and it takes like 6 to 9 months to do an iteration in a wind tunnel. And so you just can't do very many iterations. But basically today we've got digital wind tunnels, and you can do the equivalent of like an entire set of wind tunnel tests, overnight in the cloud. And so so what that means is you come up with a much better design aerodynamically. Now those designs tend to be very complex shapes. Like if you look at our airplanes, there's hardly a straight line anywhere on the airplane. And how do you build that? If you built it out of aluminum, it would be extraordinarily difficult to get the precision shape. You need like a military-sized budget for the production tooling. But if you build out of carbon fiber, you can make an entire airplane that is a custom, complex shape, tip to tail, very precisely. So basically, you mold carbon fiber, so you can just make the mold any shape you want. So we've got an optimized aerodynamic design through a whole lot of digital iteration, but then we can actually build a real airplane that embodies that shape efficiently in carbon fiber. Also, carbon fiber can be a little bit lighter than building out of metal. And then the third big one is propulsion. So Concorde had converted military engines with afterburners that were loud and inefficient. And today we've moved on to an architecture called a turbofan. And one of the other mythologies is you need afterburners to go supersonic. You don't. You just need to have more thrust than drag. And anytime there's more thrust than drag, more push than push back in a way, the airplane's going to accelerate. So it's just a matter of having enough engine power, and you can do that with a turbofan. You don't have to have a turbojet or a turbojet with an afterburner. And that makes the airplane quieter, more fuel efficient. So you put those 3 things together, and then you throw in a lot of improvements in computing as well. So Concorde, for example, is very famous for a droop nose. So the nose pivoted up and down, and like why? Because the airplane needs to be long and skinny in cruise for aerodynamic reasons. And because it's got a delta wing, it lands with a very high nose up attitude. And what that means is it comes in kind of like this, and the nose is in the way of the runway view, and so you can't see the runway. So Concorde was born in an analog era, and so what did they do? They had a mechanical moving nose. The nose would have to move so the pilots could see the runway. But I sometimes I joke that we have the first practical application of augmented reality. So we have a camera system on the airplane, and the pilot has a screen in front of them that basically they can press a button, and the screen sort of like flips over digitally from an artificial view to a camera overlay view, and you have a virtual window through the nose, and you land looking at the screen. And it turns out that works great, and then you don't need all the mechanical claptrap. It saves weight. And it makes the whole airplane more efficient.
And I would encourage people to go to the website and check this out, because it almost looks like this crazy, super futuristic headset that people can wear, and you could kind of see. It looks like a spaceship more than an airplane, just based on the renderings from the website. But what I wanted to ask you is this idea of first principles thinking, where traditionally you can kind of reason your way by analogy to creating something that has been done before. But in this case, where it was 50 years ago, there's no old technology you could take. And I'm assuming that also means you can't just buy a motor off the shelf. You can't just go to a manufacturer and say, hey, I want a piece for my supersonic aircraft. You kind of have to build all this from scratch, which people who aren't familiar with manufacturing, the reason there's recently been a lot more software progress than hardware is really hard. And that's a super difficult challenge. So I'd love for you to kind of explain to everyone how you were able to build this.
I think we need to stop saying that manufacturing's hard.
I like it. Okay.
It's actually just not true, and it becomes this like self-perpetuating falsehood. It's different than software. It requires different approaches. But we flew 3D printed parts on the XB1. There's going to be more of that on Overture. It doesn't. Manufacturing's hard, but by the way, so are LLMs and AI.
Mm-hmm.
So and by the way, those are way more capital intensive than airplanes. So I think there's a lot of like false mythology about deep tech or frontier tech or what people call moonshots. And by the way, I hate all those terms. It's just tech, and tech has different domains. The thing about hardware is if you do it traditional ways, the development and iteration cycles become very long. And one of the most important things to do is to really work on building more iteration and shorter development cycles and easier, and reducing basically make hardware look a little bit more like software in terms of development cycle. And then that turns out to unlock the ability for a small team with a small budget to do what traditionally took big teams and gigantic budgets.
I'd like to take some time and actually place us in the arc of Boom. Right now, you guys have successfully done a test run of a prototype, a scaled down version of the future cruise airliner that you guys want to build. Where are you in development arc, and what's next for you now that you are past that hurdle? And then we can talk about timelines of when this cruise airliner comes actually into production.
Yeah. So what we've done so far is we've proven we can build and fly a supersonic jet made out of airliner ready technology. We've proven we can do it. That's the XB1. We've proven we can do it in a way that doesn't have a sonic boom that's heard on the ground, which, by the way, that's a software fix, not a hardware fix.
Interesting.
And we've proven that the specific thing that we're building has product market fit because we have 5.5 years of production in orders and pre-orders from United, American, and Japan Airlines. And by the way, that's
existing airlines have already placed orders for the future airliner that you have not yet built.
That's right. We've got 130 airplanes on order and pre-order. That compares to only 14 Concordes that ever carried passengers.
How did you convince all these airlines to pay? Or is it refundable? Like, what happens if you don't?
No, they have like modest but significant non-refundable deposits, and that keeps as we hit milestones, that goes up over time.
Okay. Oh, I see. So as you get closer to in production, more of the capital that they promise, that they deposit, gets put into your company so you can continue the process.
That's right. Yes.
Okay.
So that kind of ramps over time. So we've basically, and this is one thing I think that needs to be in the hardware startup playbook is, so in the software internet world, it is inexpensive to test whether an idea has product market fit. And I think people sort of learned that making theoretical arguments about what products will be good and what products won't be good it's very difficult to judge. And because you can ship an MVP usually very inexpensively, the implicit approach in the software internet world is, if you want to know if your idea is good, we'll just build an MVP and ship it, and then you find out whether people want it. And that, there are lots of internet businesses that sound like terrible ideas, like summon cars driven by strangers from the internet to give you rides, or sleep on somebody else's couch in a foreign city. Like, doesn't sound like good ideas, but that's Uber and Airbnb, right? And it doesn't take a lot of capital to test whether people want to do it. We cannot, in order to test whether people want our supersonic jet, we can't build it and then see if anybody wants it. It's too expensive. It takes too long. So we have to have another way to, in a very rigorous way, to demonstrate to ourselves and, of course, to our investors that what we're building has a substantial market. And so pre-orders, I think, are the key mechanism for that. You got to get customers to actually put money to say, if you build this, I want it. And how do we go about doing that? There's sort of bespoke stories about our first pre-order, which was Virgin, all the way through to United American were the first ones to make deposits, where we had to create a reason that the airline would move now, versus take a wait and see approach. For example, United. Who I'm incredibly grateful to United. They've been amazing partners on this, and I think it's watch that airline. They're going places, literally and metaphorically. They ordered supersonic jets during COVID, while every other airline was like retiring airplanes permanently. And it was very much Scott Kirby and Mike Leskinen that were the sort of financial and CEO duo on that had the vision for it. And what they realized was they wanted in a crisis that was their opportunity to actually position the airline to be the best airline of the future, and so they invested in everything new, and they made a small number of strategic bets. So they did they made a bet on air taxis with Archer. They made a bet on Supersonic with us. They've done a couple more since then. That brand wise positioned United for the future, got their customers excited. Like when United announced their supersonic order in what was it, 2020, 2021. There was this massive outcry of customer happiness. Like it was, we saw the numbers. It was the most successful announcement they'd ever done by a factor of 5. Measured by passenger happiness. Because people were like, holy crap, we want this supersonic thing. And so there were already passengers switching to United because they wanted to be first to go supersonic. We hadn't even built the airplane yet. In fact, we hadn't built any airplane yet. That was before XP1 had flown. So it created an environment where there was a near-term payoff for United for them to bet on us. So we needed them to see that. And we needed them to have enough belief in us that they thought it would be worth investing in their brand, and they sort of trusted they could do it. And it required the right leadership at United. So all that was kind of in the soup. And I could tell you the story about every other deal, and they're all like slightly custom.
What did it take on your end of things to get deals over the line? Because I would imagine if I'm in charge of this deal on United or like JetBlue or any other side of things, I'm seeing this guy who worked in Silicon Valley for most of his career, doesn't like bootstrapping his own aviation knowledge and doesn't come from the aviation industry. How did you actually do the sales? What magic did you have that got them over the line?
I'll answer this in a couple different ways, but there is no substitute for actually knowing what you're talking about. Like sometimes people ask me, how did you have credibility in a domain that you didn't have any background in? And the answer is by actually being credible, not in a credential way. As credentials are useless, throw them out, ignore them. But like, I got to the point where it's very hard to ask me a question that I didn't actually understand the answer to. And so
you did the work. You put in
the
homework.
work. Yeah, there's no shortcut. And like sometimes people think sales are like some magical dark art of persuasion, where if you have the like salesperson with the right personality and the right like tricks that you can like trick people into buying your stuff. No, make something they want and give them a reason they should do it now. And then all you're counting on is their own rational self-interest and their own ability to see the truth that we see. So I think sales becomes is a communication exercise relevant to the customer's context. Like, why is Supersonic good for United to do in that moment in time? And what had happened was they actually did the Archer deal first. And we sort of started a dialogue with them, and it was kind of moving slowly. And then they announced that they were ordering the air taxis. And I thought, that's pretty cool. They did that. Maybe they should have supersonic jets too. So I called our contact back and I was like, would you explain to me the logic of why you did the Archer deal and how it worked? And and it was his deal. He was like very proud of it. So he was happy to tell me all about it. And I was like, do you think something like that could work for Supersonic? And he said yes. And I think it was like 8 weeks later we announced the deal.
8 weeks. Wow, that feels
something
fast.
like that. Might have been 10, but it wasn't like years.
Right. Yeah, airlines are not typically a category of company that I consider to be like risk taking. So it's pretty interesting that airlines are like interested in making these style of bets.
Well, I mean, I think you have to engineer the deal such that they're actually not taking a lot of risk, right? So the deposit was big enough that it was meaningful to us, and small enough to them that they could think of as an investment. And we had to earn their trust enough that they weren't worried they'd look like idiots for betting on some supersonic startup that didn't know what it was doing. And so we had to go through due diligence. And they United sent their test pilots to do the due diligence. It's just by convenience, luck, that all the United test pilots are based in Denver. So they could just like come down and see what we were doing. And they met with our technical people and they met with our test pilots. And this is lucky on multiple levels because also like every pilot wants to be Maverick and fly Mach 2.
Right.
So the pilots are really looking to say yes, and they'd literally love to fly this airplane. So we the people doing the diligence really wanted it to work and wanted to support it and wanted to be involved, wanted to fly it. So that helped too.
Okay, so
but again, there was no like fooling them into this, right? Like we had to actually know what we were doing. Right. And when people dug in, it had to be clear that we knew what we were doing.
Right. So you have the capital from 140 pre-orders is the number that I heard you say?
130.
130 pre-orders. I don't know if the details on how much actual money that is public or not. If it is, I'll ask you to share those details. Then you also have raised from investors. So you have some amount of base that I'm sure is giving you some amount of comfort. How has your perceptions of this is likely to fail as a company changed since you started it? Do you feel pretty comfy today? Like where are we at in level of risk?
It is, if it doesn't work, it will be because we screwed up the execution.
Cool. That must feel good as a comparison to where you started.
Yes and no. The first 18 months on this were actually psychologically very easy because I thought it was just so flat out impossible that I thought like there's no way. Today will be the day that I find the bug in my spreadsheet. There must be like an off by 10 error in here, factor of 10 error in here somewhere. Because it could not possibly be that in 2 weeks I'm the guy who found this formula that creates a supersonic renaissance. It just seemed implausible. And then after about 18 months and having like hired some people and having kind of, this has gone through gone through scrutiny with a bunch of people who knew what they were doing. And I'm like, if there was a bug in the spreadsheet, I would know by now. This is all doable. The question is whether I pull it off or not. And then that actually became much heavier for me personally because I now felt a lot of responsibility to get it done, and I still do. And in some ways, it's actually much, much harder now. Again, psychologically, because again, it is definitely possible. The company profile is pretty high, and sometimes I say to the team, we are definitely going to have impact. I would just like it not to be a crater.
Nice.
And so if Boom, already I get notes regularly from other entrepreneurs who say, oh, I decided to do this other more ambitious thing because I got inspired by Boom. And I love that we get to have that impact. I love that we get to inspire other people to think bigger. And yet if we screw this up, we could have the opposite effect where, and then, last time the world screwed up supersonic flight, no one tried for 50 years. I can't let that happen. We can't screw up Boom and then have another 50-year hiatus in supersonic flight. So I just can't let this fail. I have to make it work. I'm
hopeful that the enthusiasm and optimism is contagious enough that even in the case that it doesn't all work out, there will be people that now know it is possible and will try to do it.
I would hope so, but it really the world is not always good at drawing the right conclusions. There's a little funny side story here. So I have 4 relatively young kids, and at one point, I think he was about 8. One of my boys went through this phase where he was lying a lot, and at first, at first I took a very moralistic approach to this. I was like, that's unethical. You can't lie. You have to tell me the truth. And that didn't make him feel better. He just got even more ashamed. And eventually I got curious about what was motivating it. And what was motivating it was he was covering up mistakes that he was embarrassed about. And so what I had to do in the family was to normalize making mistakes. And so, we had been doing these gratitude routines at dinner. It's share something you're grateful for. I was like, guys, we're doing something new today. We're doing a mistake I made and lesson I learned. I'm happy to go first, but anybody want to go first? And it turned out they all wanted to go first. And they'd all talk proudly about what mistakes they made and what lesson they had learned from it. And one of the sort of things that came out of this that I didn't expect was I got to edit their learnings, because sometimes the conclusions were like, wait a minute, hang on, that's the mistake, but that is absolutely not the conclusion you should draw. Let me help you draw the right conclusions. And then it took me, I'm just enough of a dummy. It took me 2 years before I realized I should also do this at my staff meetings, and that this would be the part of the solution to getting executives to be more open and honest as well. But it creates that same dynamic, because it is actually pretty common, even for adults or the world at large or kids, to draw the wrong conclusions from experience. And if you can make that an explicit, open conversation, it goes much better.
I love the idea that you're really just constrained by a mindset. And I'm very curious to understand your mindset when it came to designing the actual aircraft. I'd love to hear how it works, how it functions, what form factor, what's new about this, because clearly it's going to look very different than a traditional airplane, I would assume. So how is it different and why?
Well, okay. So what does it actually take to go supersonic is maybe the first question. What is supersonic? So let's start with what is supersonic, and then we'll talk about how you make an airplane that flies supersonic and what it looks like. So the speed of sound, the best question nobody asks is, what does the speed of sound have to do with an airplane? As at some level, this seems like a very random thing to be connected. Mm-hmm. But once you remember that the speed of sound is the speed at which a pressure wave moves in air, it starts to become more plausible there's a connection, because airplanes are all about manipulating air pressures as they tap dance through the sky. And so if you're flying less than the speed of sound, if you're flying subsonic, then there is a pressure wave. Whenever the airplane kind of goes forward, it bumps into air. And the pressure wave, there's basically a pressure wave ahead of the airplane that is going faster than the airplane. You can sort of think of that as there's a little soldier running in front of the airplane saying, hey, airplane coming, start moving out of the way, air. And so by the time the airplane hits air in front of it, the air has already started to move out of the way. Now, if you are flying supersonic, what that means is the airplane is outrunning the pressure wave. And so the air in front of it has no idea it's coming. And, sort of imagine you're at a party or something. There's a group of people talking to each other, and you're this crazy person, and you're going to run at them, and they can't see you coming. So what's going to happen? You're going to crash into them. They're going to topple over like dominoes and kind of bump into each other. That's exactly what air does. So when a supersonic airplane flies, it creates these little bands of compressed air called shock waves. and those kind of stack up on top of each other as they travel from the airplane towards the ground, and that there's like stacked up little compressed airwaves. That's what creates sonic boom. So how do you make a supersonic airplane? Well, you have to be able to have more thrust than you have air resistance or drag, and drag goes up as you approach the speed of sound because energy goes into those little it goes into compressed airwaves that you don't create when you're subsonic. So there's this extra drag you have supersonic that you don't have subsonic. So you need enough power to have some of that energy go into those shock waves. And then also the physics of stability change. So the faster you fly, the more what's called the center of lift moves backwards. And so you can kind of think of an airplane as sort of like a balance. And weight is pushing down effectively at the center of gravity, and lift is pushing up at some place called the center of pressure. And so if you keep the center of gravity in the same place, and but the center of pressure, center of lift moves backwards, that means the nose is going to drop and the airplane's going to want to dive. And this is why, like before Chuck Yeager's first supersonic flight, there was this sort of the talk of there being a sound barrier, and as some pilots would approach the speed of sound, their airplanes would start diving. And of course, because of this center of lift change versus center of gravity, and of course, if you're in a dive, then you're accelerating even more, which makes the aerodynamic change even greater, and then it results in an unrecoverable dive. But this problem was solved in the 1940s once it was understood. So you have to have an airplane design that minimizes the energy that goes into these compressed air bands that can also balance across a wide range of speeds. So that results in an airplane that's kind of long and skinny relative to subsonic planes. The wings are a different shape. They're what called delta wings. So kind of triangular wings. And those are efficient at supersonic speed. But to keep the drag low, you kind of want to have them be much shorter than subsonic wings. And then that leads to kind of different physics for how you generate lift for takeoff and landing. So there's lots of little things that are different. Now, if we just say like, okay, great, what about the passengers? What are they going to experience? We want to make this the best experience in the sky. And for maybe 10 years before I started Boom, I'd like walk onto an airplane and kind of just be aghast at the like lack of design care that is in today's airplanes, from like all the seams and gaps to like, by the way, if you look at the underside of the overhead bins, next to the window seat on every row of every subsonic airplane, there's a little dark spot. Why? That's because when people stand up under the overhead bin, they bump their heads, and their head schmutz ends up on there, and the airlines never clean it. Sorry, you'll never be able to unsee that.
Nice.
Or like how many seams and gaps are there from the outside of a window to the inside? Is the PA volume ever correct? No, it's always too loud or too quiet. And so, I used to ask myself, like, what would an airplane be like if like Johnny Ive had designed it? What if it was done with the care of like, Apple in its greatest days? And so we sort of aspire to do that. And so we've got a relatively like small, skinny airplane, but you'll never know. The boarding door is bigger than the boarding door on a 737. The airplane is actually bigger in the front and skinnier in the back for aerodynamic reasons. That helps minimize some of that shockwave drag that we were talking about before. But it leads to like some really it's a very interesting canvas in which to paint a passenger experience. And so what happens? Well, we put the boarding door where the airplane's biggest. So you walk on, on Concorde, you have to duck to get on board and then like squeeze your human through like 3 rows of like floor to ceiling equipment racks with a narrow aisle. Like you're not even in your seat yet, and you're convinced the whole airplane's tiny. So we think about what's the first impression, and it's like 8-foot ceilings when you step on, like cathedral ceilings, and then the back cabin, at the back of the airplane where it gets skinnier, the very last row is the size of a G650. So the worst place in Overture is like the best private jet. and it's a 1+1 in the back. So one seat on each side of the aisle. Every seat's a window seat and an aisle seat. You don't have to choose. It's really nice and really private back there. So first class is actually in the back. And then the front cabin, I can't tell you the secret yet, but the designers and the engineers got together. And I think this is, again, the magic you want culturally is designers that think like engineers and engineers that think like designers. Because we had that, and because we were building our own engines, all of those turned out to be important constituent things. We've got something crazy in the front of the airplane that I think people will walk on and see like, wait a minute, you did what in a narrow body supersonic jet? And it's because we were willing to change the design of the airplane ever so slightly to make the interior amazing. And it won't feel small. It'll feel really spacious.
As you were hopping into Riverside, where we record this recording room, Josh and I were going back and forth on like how we think the seat map for the Overture is, because it's a topic of great. It's a good conversation that many people are having, because as you've alluded to, you know it, but few other people know it. So we were just trying to go back and forth on what that map actually looks like. Can you go into the economics of a ticket or of a seat? As you alluded to at the very beginning, the Concorde failed because it wasn't, economical. It wasn't really a profit-oriented, business-oriented machine. This is what you are building Overture for. Yeah. Can you just go into the philosophy on the cost of a seat or the cost of a ticket?
Yeah, so kind of punchline up front, New York, London, round trip, the break-even fare is about $3,500.
Okay.
Which is a lot less than people pay in business today in many cases. So that's the break-even with 80% of seats full. And that includes all the costs, like rent on the airplane, maintenance, fuel, catering, crew, everything, credit card fees, like it's all in there. So any dollar above $3,500, the airline's making money. And that means, but people will routinely pay $5 or $10 for a round trip business class ticket today. And this is another reason why United, American, et cetera, like ordered these airplanes, because they looked at the economics and they're like, oh, we will make more money when someone flies supersonic than we do if they fly subsonic. So it makes sense for us to have this as like, the thing that's even more at the front of the airplane versus business class today. You can kind of think of it as like a new cabin. It's like so far in the front, it's actually a whole different airplane. So how do these economics work? So when you go faster, you do burn a bit more fuel. But the thing that a lot of people overlook, and I think in part because Concorde never really achieved it in practice, is if you have designed the airplane such that there's going to be a lot of demand for it, it can fly as many hours a day as you'd fly a subsonic airplane, but because it's twice as fast, it could do twice the flights. So, right? You can, so in finance terms, you can sweat the asset. And we call it the speed dividend, right? Because if the airplane's twice as fast, you can do twice the flights with the same pilots and crew. Catering costs drop, as you don't eat as much on a short flight as you do on a long one, right? Maintenance is generally proportional to hours of use, not distance flown. So many costs about flying are per hour. And so all the costs that are per hour get cut in half.
Wow.
Right? It turns out that if you look at the pie chart of operating costs, the slice of fuel gets a little bit higher. All the slices that are, per hour get smaller, and it all sort of balances out. And Concorde never achieved that because they were so far out of pocket on fares and comfort that the thing was, with even a small number of flights, it was flying half empty. So they never got the utilization to work. But that wasn't inherent. It was just the amazing technology, but commercial fuck up.
And are there different kinds of seats in the Overture, or is all the same seat, or is that up to the airlines? How does that work?
So we are handling this differently than Boeing and Airbus do. Boeing and Airbus, they make a tube with wings, and then the airline specs the seats, buys them separately, and like Boeing will like install whatever seats the airline chose and give the airline the airplane. And I guess theoretically someone could do that with us, but because of our sort of design forward, passenger experience forward, philosophy, we expect almost every airline to buy the interior that we created, and they'll be able to customize it put their colors on it, put their feel on it. But I think there will be a little bit of a inversion of brand hierarchy versus how it works today. So think about phones before the iPhone. Generally, consumers picked their carrier and then picked their phone.
Right.
And they didn't really care that much about, like, was it a Motorola or a Samsung, right? Mm-hmm. And then the iPhone came along, and it was so different for consumers that people picked the iPhone, and then they're like, well, I guess it's AT&T, because they had an exclusive. And the fact that people were so hungry for the Apple experience enabled Apple to have a lot more control over that experience than versus like all these other phone makers that were basically building whatever the cell carriers told them to do. And I think there is a strong parallel between Overture and iPhone in a lot of ways, including how it changes the relationship between the manufacturer of the airplane, the airline, and the passenger. And so, we see ourselves as having two customers: the airline, that's like our operating partner, and it has to work really well for their pilots and their crews, and maintenance has to be good, and it has to be reliable, like all the things it has to make money, it has to do all the things that airlines care about, but it also has to do all the things that passengers care about. And so we work directly with passengers, and we work directly with every contingency, every stakeholder group inside the airline.
I like the way you kind of reference the iPhone. It feels similar to how you build this, where there's a very tight-knit group between engineering and design, and that allows you to iterate fast. I'm curious what that iteration process looks like as you kind of make your way to the commercial aircraft. So you kind of have the XB1, you have the test version. We are going to get to the large version with 64 plus seats. What does that process look like getting from test to production?
Yeah. So I think one thing that's important to note that's different between airplanes and typical software products. So great software is loosely coupled, meaning you can break it down into modules, and the implementation details of one module are not relevant to the design of any other module. You kind of just define the interfaces, and if something you change in one module changes the behavior in another module, like your software was bad, it's not supposed to happen. But airplanes are the exact opposite. They're very tightly coupled, very integrated machines. And they involve trade-offs between disciplines. Like the best wing structurally is thick, the best wing aerodynamically is thin. The most aerodynamically efficient airplane it will have attributes that cause it to be very loud at takeoff and landing. So there are all these trade-offs, and and if you go add weight in the nose, well, something has to balance that weight in the tail. So the level of integration is high for an optimized machine. So collaboration is really important. We have a cultural principle we call invent together, and invent together means every team member has the responsibility to be curious about every other discipline and to teach others from other disciplines what they see from their discipline. So this is not some legacy players have this approach where they know they're done when everyone's equally unhappy. And they've got, the aerodynamicists are supposed to advocate the most for aero, and the structures guys are supposed to advocate the most for structure. And then some chief engineer comes in and makes a decision, and then everyone leaves the room grumpy because they all lost. And, and we try to take the exact opposite approach culturally. Everybody understand everything else, at least the basics, and then optimize for the whole. So culturally, that's really important. The passenger experience innovation that I've sort of been hinting at but not disclosing, it came at the expense of airplane performance. And the first iteration of it cost 1,000 miles of range, which is just, you can't lose 1,000 miles of range in a 4,000 mile airplane. You got to get it back. But we looked at it, we're all at the end of the day, we're all passengers. We know which airplane we want to fly on. Let's go find 1,000 miles of range. And so by negotiating the details of exactly how to fit the cabin in the airplane, and then co-optimizing airplane and engine, those groups talking to each other, working together as one team, we found 1,000 miles. We got it back, and we all get the airplane that we're very excited to fly on. So that collaboration is, is actually deeply important. It's not just corporate speak. It's fundamental to how we create the product. And now, so how does the iteration work? So the engineering team operates on like an agile process. We run development cycles that are 3 to 4 weeks long, and we do sprint planning. So there's a lot of like agile, Scrum like process. There's daily stand-ups, and the and then there's sort of that kind of gets you iteration to iteration. What about longer term? You need something longer term. So there is an overall kind of like project plan that we expect to evolve and change. And we have something we call mission success events, MSEs. And MSEs are the like intermediate milestones that all have some, that are like evidence that we're getting closer and are something the team can celebrate on. And so every Monday morning at 9 a.m., the entire company has an MSE stand up, and every MSE owner briefs where they are in their MSE, and they're all red, yellow, or green. And if they're yellow, like we rally around them and try to help them out. We try never get to a red. If you make yellows socially acceptable, you can avoid reds. And then we encourage everybody to sort of build iteration into how they're approaching things. So the classic way airplanes get developed in the like modern era is you go straight to a production design. And the first airplane that you ever build, it will get tested and then get delivered to a customer. And so it has to be, the final design. Ooh, boy. So now that sets a really high bar. And by the way, the bean counters love this approach because it generates project plans that look faster and cheaper on paper. You take all the things called prototypes and you delete them from the plan. Oh, we can remove time and we can remove cost. So the plan looks better on paper, but it never looks better in reality because the first thing is never right. But by the way, if you've planned for it to be perfect, now you've also planned for it to be almost impossible to change. So this is where and this is the story of every airplane program and every engine program out there. Like it looks great until it suddenly looks terrible, and there are all these unexpected problems found only at the end when they're like very expensive to deal with. So this is the 787 was like this. The first airplane ended up being junk, but had all the cost of it not being junk. The engine that's in the 777X, which is still not done, like Boeing, GE deleted all the like prototypes and test articles along the way. Tried to nail it the first time. Guess what? They didn't because they're human. And now all of a sudden the engine's late and hard to change. So we are, we told the team, assume that hardware is cheap and work to make that true and plan that they're going to be many iterations. And so we're building a pre-production, the first Overture that will roll out, hopefully in about 2.5 years, will be a pre-production prototype that will never get delivered to a customer and doesn't have everything on it that the final production airplane will have. But has enough on it that we'll be able to learn a lot. And we also told the team, by the way, by the time we roll out the D1 airplane, that's what we call it Development 1, by the time D1 rolls out, the D2 should be like mostly built. Because just in building D1, we'll have learned a lot of things we'll want to change. And those could go on D2. And the other thing that, so things that make safety critical airplane engineering slow, if an engineer is worried about hurting somebody, they're going to have to be very careful, very diligent, kind of slow. Or if they're worried about breaking something that's hard to replace, they're going to be slow because it's like safety of asset. And we learned this the hard way on XB1. Like we had this, these like flight control actuators that turned out they were $60,000 each, so they're expensive. But that wasn't the worst thing about them. The worst thing was that they were both fragile and it took a year to get replacements. Oof. And so we got to a point where we had like one spare and nobody wanted to be the engineer that broke the last thing and grounded the airplane for a year. Because that probably would have killed the company. We'd have to like lay everybody off and like, all find other jobs for a year and come back. Like, I don't know if we would have survived that. So it took us like weeks to even do testing because nobody wanted to like screw the test up and break another one of these things. So we have a rule, which is we don't allow anything that's difficult to replace on the airplane, and we plan to build multiple prototypes. So we don't have to worry even about the airplane being hard to replace. And this doesn't mean that we're going to like willy-nilly crash jets. Like there's a safety bar. We have to meet the safety bar. for human things, but you want to minimize the scope of safety critical engineering. You want to make everything else kind of expendable in the development path, and then you can iterate really quickly. Another thing I'll mention that's sort of in the development philosophy here is I believe in success-based schedules, and I believe in speed over predictability. So again, traditional aerospace, everyone gets judged on like do they deliver when they say they're going to deliver, and so if there's high punishment for missing a date, now everybody sandbags their estimates, right? Because they don't want to be late. Nothing ever gets done in less time than somebody forecasts. So if there's a thing that really should take 3 days, but it might take a week, a week goes into the schedule and it takes a week. And because people are, someone today said, nobody does until it's due. There's no due until it's due. So all the 3-day effort actually starts at the end of the week. And if it turns out it's going to be a week, then it actually takes longer than a week because you started it late. And so even when you sandbag schedules, you miss them, and probably you miss them more because everything is off by a greater percentage. So we say, look, we make all of our schedules success based, and assume that we can find a way to do it more efficiently, modestly more efficiently than it's been done before. And then when we find we run into a problem, then we rally around the problem and find the best way through it. And so this results, I think, in the fastest actual execution, the lowest cost actual execution. But it doesn't. We don't know on day one exactly when everything is going to get done. And I try to versus like when I used to try to do it the other way. I'm like, I need to hold teams accountable to dates, and like here's when it's going to fly, when it's going to roll out, blah 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 blah. And then we spend an enormous amount of energy trying to get those right, having morale issues when people didn't believe in the dates. And then all the wasted energy into arguing about how long something was going to take when really nobody knew. And what we should have put our energy into is moving fast and efficiently.
There's a lot of process engineering I'm seeing going on behind the scenes at Boom. Yeah, which I mean, if you're going to break through not just the supersonic barrier, but the barrier that has seemingly plagued the airline industry for the last 50 years, I think that's what it would take. Josh, so we know that the end of Overture, at the tail end of Overture, it's 1 seat by 1 seat. That's what Blake said. He said that's where the first class seats are, implying that as you move up the aircraft, it's no longer 1 seat on the left, 1 seat on the right. There's something in the front of the aircraft that he thinks is so cool that he's willing to shave 1,000 miles of range that he had to go find elsewhere. And so I'm trying to figure out what is in the front that is so revolutionary, because it's not going to be some pattern. It's not going to be like, oh, it's 1 by 1 in the back and 2 by 2 or 2, 1, 2 in the front. It's something odd and unique, and I think not found in any other aircraft. Do you have any ideas? What do you think is up in the front?
Do I have any ideas? I can't imagine. Well, the last new airplane was designed, like 30 years ago. So we have to assume, okay, given all of these new constraints that we have, it's going to look different. It won't be 3 seats in a row, 2 seats in a row. Could they be faced backwards?
Yeah, I was thinking maybe it's diagonal? Like a room. Maybe there are seats around a table.
The G's from going fast kind of like might push you forward. I don't really know how that works.
It's not that crazy. So the obvious thing you could do is a 2+2.
Right.
Right. And that's
I don't think you would be excited about that. So excited to bring it up.
Look, I'm not going to tell you the answer, but like if you start to think about what's wrong with a 2+2 and what the downsides are, and what passenger value you want to create that's better than 2-2, then you can kind of start to think of maybe some ideas, and then what you'd find is if you took the front of the airplane is about the same size as a 737. It's actually bigger in some places, but if you think of the thing that's better than a 2-2 and you try to fit it to 737, it actually doesn't fit. It very slightly doesn't fit.
Okay, these are good
but then there's a way if you really to change the airplane.
Okay, starting to paint a picture. Now I have an additional question, which is now surely that you figured out supersonic flight, you can start rolling this out as soon as they're built, right? Is there regulation preventing this from happening? And could you explain what it is and why? Yeah,
so you're talking about supersonic over land, right?
Supersonic over. So, like, when am I going to be able to go from New York to LA in like half the time?
I mean, if we deliver the airplane when we're targeting to deliver the airplane, which is 2029, then it'll be like end of 2029, being your first passengers. But yet there is still this regulation that we talked about before. It's the Federal Aviation Regulation, Part 91, Subpart 817. It's my least favorite number.
Yeah,
91,
it sounds like
817.
the bane of your existence.
Bane of my existence. I think its days are numbered. There was a bipartisan bill introduced just a few weeks ago in the House and the Senate that basically says, FAA, go fix this. And
the bill says that.
The bill says that. It's a simple bill.
What does go fix this mean in like Congress speak?
So there's actually an important regulatory principle here. The what you don't want to do is get Congress in the business of like specifying specific things like decibel levels. But you want Congress to be able to provide principles by which rules should be written. And so the way Senator Ted Budd from North Carolina introduced this on the Senate side, Troy Nehls introduced it in the House side, and it's the same bill in both places, which is important. And what it basically says is, FAA, you have, I think, 12 months to go revise 91-817 such that a supersonic airplane that flies safely without a boom reaching the ground is allowed to do so without any special permissions.
And your boom is not reaching the ground.
Our boom does not reach the ground.
I'm not sure we explained that either. So how is that even possible? Because that hasn't happened
we should talk about
in the
that.
past.
It's really cool.
I'd love to understand how this works.
So that classically, people have talked about solving sonic boom not through eliminating it, but by dampening it. And so like there's a NASA project called X-59 that's trying to build an airplane that demos this approach. And it results in these like really bizarre, difficult to build and like nearly impossible to scale airplane designs that are like, they get even extra longer because they're trying to spread the shock energy across like more time, which makes it sound quieter. And they're trying to get like compression waves that cancel out with expansion waves. It's like a flying Bose noise canceling headset. It's really complicated. And it's hard to make it work in all conditions. But it turns out there's a much simpler answer, which is a software fix. And it depends on refraction. And so what happens is all waves refract when they go through something where the speed of propagation changes. So let's think back to like high school, middle school physics. We've probably all seen that little demo where there's a glass of water and then you drop a pencil in the glass of water and the pencil looks broken.
Ah, yes.
And like why? Well, it's because the light bends when it goes through the water. Why does the light bend when it goes through the water? Well, the speed of light in water and the speed of light in the air are not the same. And the light refracts, it bends towards where the speed is lower. And the intuition for this is, imagine you're driving your car and the wheels on the left side of your car are going slower than the wheels on the right. You're going to turn left. Right? So waves do the same thing. They turn towards wherever the speed's lower. So, okay, the speed of sound is not the same everywhere in the atmosphere. The speed of sound is actually a function of temperature. So when it's colder, the speed of sound is lower. And when it's warmer, the speed of sound is higher. So Mach 1 in miles per hour is a different number at altitude than it is on the ground.
Right.
And so, okay, so low speed of sound, high speed of sound, low. Waves turn toward where it's low. Waves turn upward. And so you can think of what matters is if you fly the airplane at the right speed and the right altitude, the boom will basically come off the airplane at a shallow angle and make a gigantic U-turn in the sky. So if you're high enough, the bottom of the U never touches the ground.
It's like the Earth's atmosphere protects the sound from getting all the way down.
That's right.
If you do it at the right angle.
That's right. And
it bounces off the atmosphere.
Yeah, it makes a U-turn in the atmosphere and it kind of like goes up towards space and it can like ricochet around. But by the time it ever possibly hits the ground, it's like hundreds of miles away. It doesn't sound like anything anymore.
Right.
Like it just totally dissipates. So to do this, what you need is a ray tracing algorithm. like a bunch of things in supersonic flight turn out to be enabled by algorithms that were developed for computer graphics. And this is one of them. So basically taking current real-time weather data and you run a whole bunch of ray tracing simulations at different speeds and altitudes, and you find you basically find the fastest speed you can fly given the weather of the day, and then you have an autopilot that flies that speed. And so long as it's got engines that are powerful enough, any supersonic airplane can do this. It's not just ours. So people keep thinking, because NASA's doing this complicated airplane design, people assume we did something aerodynamically. No, and we didn't even plan to do this on day one. And we sort of stumbled into it. And a thing people overlook is like, yeah, when we flew supersonic for the first time, when you go watch that webcast, there were actually 3 airplanes in formation, and none of them made a boom. Why? Because they were all at the same speed and altitude. It's a software fix.
Very cool. Very cool. So this plus this regulation, this one regulation in the FAA code, is that the only regulation that you have to deal with? It's one and done? It's a magic bullet? Or is it more of like because I'm used to regulation and government stuff being trench warfare. There's no magic bullet. How simple of a fix is this?
I mean, it's really simple.
Okay.
Like it just needs to say, so long as you fly the airplane in such a way that a boom doesn't reach the ground, it's all good.
Beautiful.
And then I think at some point there'll be a version 2 of it, which is more complicated, which is like, at what level of attenuation does a boom need to be acceptable? That's much harder. Reasonable people will disagree on this. So the one downside to Boomless Cruise is it does limit top speeds. The average will be about Mach 1.15, which is 50% faster than a 737. So it's a good speed up. But it's not 2x, it's not 3x. And at speeds above about 1.3, the geometry just doesn't work out. So then you want to look at like, okay, can you fly high enough that the inverse square law is your friend? And then you have to decide like, okay, at what level of attenuation is it okay? And that's a question where reasonable people can differ. And I think there needs to be some really good psychoacoustics to make that an objective conversation. Like what we need to do is put a bunch of people in a room, not tell them there's a sonic boom study, have them do ordinary things like have a conversation or watch TV or do homework or, have a baby that's sleeping, and then inject into that environment a bunch of sounds. And, there's thunder, there is a Harley going by, there's a police siren, and then there's some sonic booms of different intensities. And you start to look at, say, at what level of intensity of sonic boom does it become no more disruptive than other things we have today? And I think you probably subtract 1 dB, so you can say it's better, and make that the limit. But no one's done that study. Like I've been in the NASA sonic boom simulators, and they're all biased towards methodologies that encourage more stringent levels of quiet that are harder to achieve and actually not necessary. So, but this is all future work. We don't need to do it in version 1.
Blake, you said
to be clear, the version 1 regulatory change is incredibly uncontroversial because it says if there's no boom, it's okay.
Right.
There's nothing to argue about.
It's the easiest hurdle. Yeah.
It's the easiest thing, right? So we'll go do that, and then we'll get that shipped. And then passengers will say, well, like, I want to go more than 1.5 times faster. I want to go 2 times faster. I'm going to go 3 times faster. We can say, well, if we're willing to accept this thing that's less bothersome than all kinds of other things you accept, you can spend less time on airplanes. Are you in?
Right.
And I think people are going to say, I'm in.
Yeah. Blake, you said Overture ships to its first customers, its first airlines in 2029. So you got 4 years, 3.5 years. And then that's when we'll be able to take these super fast flights.
I think that's 4.5 years, right? Because it's 2025 now.
It is 2025. That's math. That's why you're leading the company. I got scared there. I was like, wait a minute, would I lose a year? Oh shit, I got to go even faster. What is and then after that, like you still have to scale production up. So there's, that's kind of like the starting race. What's the most likely reason why you won't make it? What's the most likely reason you'll fail? The thing I say to the team every single day is the most likely cause of failure is we don't get done for an obtainable amount of capital. So we have to get really capital efficient, and we have to be really good at telling our story to investors so that wise investors will want to buy in. And then we have I can't tell you yet, but we have something that might really help with that, that we'll announce later this year.
that I think will make the whole thing far easier to finance.
You're good at
but
teasing.
The more interesting part that we could actually talk about is just the efficiency thing. Because it's a thing I consider the team that makes it very simple is if we do this the way Boeing does it, we will have a Boeing-like cost structure, and all the pundits that say it's going to cost $10 or $20 billion will be correct. And we're not going to get $10 or $20 billion here. We need to be 10 times more efficient. We need to do this for 1 or 2. Because we can get 1 or 2. We're not going to get 10 or 20. So we have to find a way to do it more cost efficiently. And I don't think I told you the story about the 3D printers and vertical integration. Should I tell you that story?
No, we haven't.
That's a good example of how you do this. So the punchline is when we were outsourcing our engine, we were going to have to pay Rolls-Royce $2 billion to build us a not very custom engine. And we brought it in-house, and we think it's going to be like a quarter of that, maybe even less. And and as an example of how you get the cost out. So we're building our first prototype engine right now. It's about 60% into the manufacturing process. And because it's a prototype, we're 3D printing parts that you probably wouldn't 3D print in production. It's part of how you iterate faster. And so we've got these like metal printed turbine blades, and we go to source them traditionally. And the supplier is like, okay, it'll take 6 months and it'll cost $1 million for one set of blades. But oof, like both of those things hurt. I was like, guys, how long does it actually take to make a turbine blade? And they're like, oh, it's actually only 24 hours. Okay, so what's going on the other 179 days? It's like, we got to wait your turn on the machine, and they're like printing one blade at a time, not in batches. And I'm like, oh, this is terrible. Because if it takes, we can't wait 6 months, and also if it takes 6 months to get blades, then if anybody ever wants to change the design, they can only change the design once every 6 months, which is worse. And so I was like, okay, well, what does the machine cost? And like, oh, the machine's $2 million. Wait a minute. For the price of 2 sets of blades, I can get the machine? Well, it must be these machines are like, right. It must be the machine is like super backlogged. It takes forever to get the machine, right? No, they're in inventory. You can get them in a few weeks. Like, okay, this is right. So we bought the machine, we printed the blades on our own machine, and we got the machine and the blades months faster than we'd have gotten them from the best supplier. And so all of this collapses cost. All of this, and it reduces the cost of iteration, right? Because if it turns out the blade design is wrong, we'll just print another set of blades tomorrow, right? And not in 6 months. And the hardware, like there's like about the physical cost of the blades is like $1,000 for an engine. It's just like some powder metal that you print, right? Like it's not $1 million; it's $1,000. And so you can the hardware is not the expensive part if you build it efficiently. The team is the expensive part. And so if you can enable the team to go fast and iterate quickly and converge on the final answer much faster because they can make many loops around the iteration cycle, the cost of all this collapses. And I think when Overture carries its first passenger, the biggest like interesting story will be the astonishingly small team and astonishingly small budget with which it was all accomplished.
That's amazing. I want to ask you about motivation for other people, because hearing these stories, it's like, okay, this seems very challenging. And then you break down the challenges and you're like, okay, wait, this kind of makes sense. You don't need to be a aerospace scientist to solve all of these. I'm curious what advice you could offer to people, because I was going through a little bit of your background and there's this crazy jump in your resume that is like Groupon supersonic airplanes. And I'm assuming you weren't equipped to build supersonic airplanes. So for people who want to be ambitious, what did that leap look like, and how can people kind of make that less intimidating to do hard things?
The mistake I made in my first company was I'd spent a few years at Amazon, so I thought I knew e-commerce, and then I'd spent a few years at a mobile startup, so I thought I knew mobile. So I thought, therefore, I should work on mobile e-commerce, and I ended up like building this mobile shopping app for people who shop in stores when I am myself an e-commerce nerd who hates stores, and yet it had all the usual startup challenges. Things are hard, existential crises. And I would get up in the morning and I think, why in the world did I get myself into this thing? I don't even want what we're building. And so what I learned from that experience was that knowledge and skills are way more variable than passion. And for me, like supersonic flight is like, it's like my life's work. Like, I'll stop at nothing to make it happen. And, but that's not for everybody. Like, but I think everybody has that thing that, like, imagine if you went back in time and you talked to your 5-year-old self and you said, hey, little David, hey, little Josh, like, here's what you're going to get to do. And if you sort of imagine, like, the 5-year-old Blake, like, if you told him he was going to get to build supersonic jets, he'd be like, no way. No, that is so cool. Like, I don't believe you. Like, I get to do that. And so that's the thing that I think each of us should try and find. And, like, what would just make our 5-year-old self tickled pink, and then recognize that we can learn. We can learn new domains. Especially once we've been around a little bit and we know how to learn. If we're by the way, startup founders are always autodidacts. Like, if you ask somebody the day of IPO what they needed to know to be successful and how much of it they knew on the day of founding, they're going to all laugh and say, like, I didn't know anything on the day I started. I had to learn it all along the way. So if you're going to learn 99% along the way anyway, why not put domain on the table for something you can learn? And work on the thing you really want to have succeed, because what that's going to do is it's going to make all the other shit worth it. Because like startups are, some days are like chewing glass. Like Boom has a near-death experience every 12 months, if not more. And I have to get through them. And like, how do I get through them? It's because I really want this to work, and so I don't give up, and it's worth the pain. So work on something that's worth the pain, trust that you can learn things, be willing to go be a beginner again, and work on the most ambitious thing you can possibly get your head around. And if every founder just like operated from that mindset, I think we'd have much happier founders in general, and way more amazing things would get created.
That's some pretty amazing advice to wrap this up on. So for the people listening, we're going to end this here so you can go and put that advice into practice. And for Blake, he's going to go continue making these planes that we have something to fly on in 4.5 years. So Blake, just wanted to thank you so much for your time, for offering words of wisdom, and for working on something so important and bringing supersonic planes back. I am very excited to participate, to be a customer, to be a user of the product whenever it's launched. And just want to thank you for everything you've done, sharing your time today.
Well, thanks for having me. This was a great conversation. So thank you.